All right, welcome back, everyone. It's fourth quarter, and that means some of you are distance learning and some of you are in person. The first thing that we're going to talk about in fourth quarter is something called the domain of rational functions. And in order to talk about the domain of a rational function, we need to know what a rational function is. And a rational function is simply a function that contains a fraction. All right, so um, it it contains a fraction, so that means that everything that we're going to deal with has a numerator and a denominator. But since it's a function, it also has an input and an output. And remember, the input for our functions is always going to be x, and the output is going to be called f of x, or the function evaluated at whatever value x is. Now, sometimes we refer to f of x as y when we're graphing functions. That's because our input is the x value, and our output then is the y value on a graph. Okay, so a little reminder on how to evaluate a function. So if we have an input of x equals 5, what is the output of the following function? And the function is f of x equals x squared minus 8x minus 20, all divided by x. So this is a rational function because it's a fraction. And all we have to do is replace all the x's with 5. So I'm going to go ahead and do that. So I'm going to write this as f of 5. So that tells me I'm evaluating the function at x equals 5. So I have 5 squared minus 8 times 5 minus 20 all over 5. Okay, so I just simply replaced every single x with a 5. And you'll notice I use parentheses. When the number is positive, the parentheses don't necessarily matter that much, but if you're evaluating a function at a negative value, then the parentheses are really important because there's a difference when we have parentheses and we're squaring negative numbers. All right, so all we have to do now is just simplify this thing. So we have f of 5. Notice how the left-hand side always stays the same. So then we have 25 minus 40 minus 20 all over 5. And I'm going to simplify some more. And again, that left-hand side doesn't change. So we have 25 minus 40 minus 20. That ends up being negative 35 all over 5. And then I'm going to simplify one more time and just simply divide negative 35 by 5, and we end up with negative 7. Okay, so the input of our function was 5. That means the output of our function is negative 7. So our output down here is negative 7. All right, so just a little reminder of input and output, what they mean when it comes to a function. So the one thing that we want to now focus on is the domain of a rational function. And the domain of a rational function is the set of all possible values for x, or the input. All right, so we're going to focus on what numbers can we put in a function. And we write the domain in set builder notation. And I don't know if you remember this or not, but in the beginning of the year, we use set builder notation, and we always start with real numbers. So I'm going to give you an example of what set builder notation is here. So you can use this to kind of as a model for when you're going to write your answers when I ask you what the domain of a rational function is. Okay, so in set builder notation, we always start off by identifying the variable that we're dealing with. Okay, so we're dealing with the variable x, and then we have this symbol that we use, which is just a vertical line, and that vertical line means such that. All right, so this vertical line means such that. Okay, so basically what we're saying is we're dealing with the variable x, and then such that, or we're defining what x needs to look like. Well, the first thing that we need to define x to be is all real numbers. So that's why it says we always start with real numbers. So we're going to say x such that x is, and I'm going to use a symbol here for real numbers, and it's a funny looking R that has two vertical lines. Okay, so it's x such that x is real, And so this is about the simplest form of set builder notation that you can start with. And basically what this is telling you is that the set is all real numbers, okay? Now, sometimes we're going to have to exclude some numbers. And when we exclude numbers, we do it because the domain of a rational function is undefined when the denominator of the fraction is 0. Okay, so we will sometimes need to exclude numbers because we don't want the denominator to be 0 because we can't divide by the number 0. In math, it doesn't allow you to divide by 0. If you're questioning that at all, and you have an iPhone, just ask Siri what something divided by 0 is, and Siri will tell you a funny story about it. So if I'm going to write set builder notation for each of these two examples down here, the first one I have to exclude some numbers. The second one, it includes all real numbers. And the reason it includes all real numbers is because there's no variable in the denominator. Okay, so for the second one, I'm just going to write the domain exactly like I did up in the example right up above. So I'm just going to write the domain is the set of all numbers x such that x is real. And that's all I have to do. Because there's no number that I can plug into this function that's going to make the denominator 0. Okay, because the denominator is 11. So if I plug in x equals 10, it doesn't change the denominator at all. It only changes the numerator. Okay, but in the first example, since I have a variable in the denominator, I'm going to have a situation where if I plug in the number 7, I end up with 0 in the denominator. And I don't ever want 0 in the denominator. So when I write my domain, what I have to do is I have to write it exactly like I did, x such that x is real. But then I have to exclude the number 7. So I need to say x can't be equal to 7, or I can just write x not equal to 7. Okay, so what this means is that I'm including all real numbers, but I'm not including the number 7. Okay, and if you think about it in terms of like a number line, in terms of a number line, we know that we start with 0 in the middle, right? And then we have 1, 2, 3, 4, 5, 6, 7, right? So I might have 1, 2, 3, 4, 5, 6, but then I don't want that 7 in there. So essentially what this is doing is it's saying we're getting rid of that 7, but we're keeping every other number on the number line, both positive and negative. All right. We don't have to worry about number lines, so I was just using that as an example to try to show you how the number 7 is excluded from the list of numbers. Okay, so we only want to do that when we have a variable in the denominator. So it's pretty simple to look at some of these and identify, okay, this first one, I don't see a variable in the denominator. So that means I can just write my domain as x such that x is real, because I can plug in every single real number into this function and get an output of some sort. There's no time when the denominator is going to end up being 0. Okay, the second one, I can notice, hey, I've got a denominator that's got a variable in it, and if I plug in the number 1, I am going to get 0 in the denominator, so I need to exclude the number 1. So I'm going to say x such that x is real, but x is not equal to 1, or x can't be equal to 1. Okay, so some of these are really simple because we can just look at it and say, all right, I know it's going to be 1. And in this case, it's always the opposite of whatever number is in the denominator. There's -1 in there right now, so it's always going to be the opposite. Now, sometimes they're not so simple because the denominator is an expression of some sort. And so what we have to do here is we have to now go back to what we learned last quarter, and that's factoring. And I'm actually going to factor that denominator. And if I think about it, if I want to factor that into two binomials, I need to look at the number 15, right? And say what factors of 15 either add or subtract to -2. So I have 1 times 15 and 3 times 5. Well, the 3 times 5 is what I'm looking for because I noticed that the difference between 3 and 5 is 2, but I want it to be +3 and -5. So I'm just going to rewrite this function now as f of x equals 7x minus 2. But then I'm going to rewrite this as two binomials factored. So I'm going to write it as x plus 3 and x minus 5. And the reason I want to do this is because now I can easily identify what number I can plug into the first binomial to make it 0, and then what number I can plug into the second binomial and make it 0. And for my domain, I need to exclude those two numbers because those are the two numbers that will make the denominator equal to 0. So if I look at the first one, I know that, hey, I can't plug a -3 in there, and this one, I can't plug a +5 in there. So those are the two numbers that I need to exclude now from my domain. So my domain is going to be x such that x is real, but then x is not equal to -3 or 5. Okay, so I just excluded those two numbers now because I was able to factor that trinomial into two binomials. Okay, so we always want to think factored form and simplified form in order to find the domain. All right, let's look at another one. So in this case, we have just two terms in the denominator, and it's a little bit different because it's not like a trinomial where we can factor a trinomial into two binomials. In this case, we have to just think factoring by GCF, and so I'm going to factor this thing. So I'm going to write it as g of x is equal to 6x squared plus 1. And then all I'm going to do is factor an x out. So I'm just going to write it as x times x plus 3. And in this case, there are two numbers that I need to exclude because I could plug a 0 in here and make the denominator 0, or I could plug a -3 in here to make the denominator 0. So my domain is going to be all real numbers. So x such that x is real, but then x not equal to 0 or -3. Oops, let me write the word or in there. Okay, so that one was a little bit different because instead of factoring a trinomial into two binomials, all we had to do was factor the denominator using GCF, or greatest common factor. All right, the next one, we go back to one that's pretty straightforward and simple because there's just a number in the denominator. So my domain is x such that x is real. So it's all real numbers, essentially. I can plug in any single number into this function because there's nothing that'll make the denominator 0. All right, and then what do we have? Just one more? Yeah, just one more. All right, this last one kind of tests your factoring skills a little bit. The thing to look at here is, say I've got a perfect square here, I've got a perfect square here. There's a minus sign in between, so that means I have the difference of squares. So I can rewrite this with the denominator factored, and I can rewrite it as x plus 3 and x minus 3. Okay, so I can plug in a -3 in the first one to make it 0, and a +3 in the second one to make it 0. So I have to exclude -3 and +3. So I'm going to write this as x such that x is real. Whoops, hold on. No, that's not good either. All right, x such that x is real, but x is not equal to -3 or 3. All right, so what you should notice with every single one of these is I didn't pay attention to what was in the numerator at all, because I don't really care what's in the numerator when it comes to the domain. The only thing that has an effect on the domain is the denominator. And when the denominator is 0, I have to exclude those numbers. So that's why I only focused on the denominator when finding the domain of these functions. All right, you have an assignment down here. So there's a whole bunch of them where you just have to find the domain. You're going to have to do a bunch of factoring. And the last two questions where it says challenge, these two questions are a little bit different because they make you think backwards and they make you think, okay, what sort of rational function would have a domain that looks like this? And there are a whole bunch of possibilities for answers because you can have anything you want in the numerator, but the denominator is going to have something specific. Um, but there could be several different options. So you may have a different answer than somebody else, but you still would have the right answer. So this is kind of a new way of thinking that I'm going to try and introduce with all the stuff that we do this quarter. And it's going to be similar to that last test that we took in third quarter, where there isn't necessarily one right answer, but it's testing your understanding of what it means in this case to be the domain of a rational function. Okay, so if you have questions on that, um, come to my office hours or email me and schedule a time to meet with me.